Okay, guys, 4.2, because I got a little long-winded, so I'll do 4.3 in a separate video. 4.2 is about vector spaces. 4.3 will talk about subspaces of those vector spaces. Should have done this before I started recording, huh? All right, a vector space, by definition here, let B be a set, and it could be a set of 2 by 2 vectors, 3 by 3, n by n. It could be a set of matrices. It could be a set of functions, set of polynomials, a set of numbers. Could be any kind of set that you can think of. So let it be a set on which two operations are defined. Now, there is a standard definition of vector addition, where you add the x's, add the y's, add the z's, dot, 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 and scalar multiplication, where each component just gets multiplied by the scalar. Those are the standard definitions of vector addition and scalar multiplication, the definitions that we've learned before many times. However, you can redefine either one or both and create new spaces, new dimensions, new universes, whatever. And as you get up into upper level mathematics, if any of you want to be math majors, you get into you can define different types of spaces where distance and things like that are measured in different ways, where a circle is actually shaped like a diamond or a square or something like that. It's really cool stuff. And this is the beginnings of learning to do that. So you will have some homework problems that redefine either addition or scalar multiplication. You'll see those in the homework. I highly recommend that you read the textbook. It's very well written, and it makes a lot of this stuff easier to understand, whereas I can only do so much in a video lecture here. So look at the book, look at the examples in the book, see the definitions, see the theorems, see the properties that are listed, things like that. Okay, so there are 10 axioms that a vector space has to satisfy. And that list of the 10 axioms are on the next page, but they're in your book on page 161. It's probably going to be easier to read them there. Okay, here's your 10 axioms. If u, v, and w are vectors in the set V, and c and d are just a couple of real numbers, any real numbers, then axiom 1 says that if you add those vectors together, you stay in the same space. So if you take, say, two-dimensional, let's use three-dimensional vectors, x, y, z. You take an xyz vector and an xyz vector and you add them together, what are you going to get? You're going to get an xyz vector. So you're closed under addition, because when you add any two vectors in the set, you get another vector in the set. Now, of course, these sets are infinite, and you can have finite sets that are closed, but for most of these problems, we're talking infinite sets, like three-dimensional space, or the set of all second-degree polynomials, or the set of all 4x4 matrices, things like that. Okay, second axiom. Addition is commutative. And if all you're doing is adding the x components and adding the y's and adding the z's, well, x1 plus x2 is the same as x2 plus x1, right? So you see that it's closed closed under addition, and addition is commutative. It's associative. There is a zero vector such that all of the components are zero, right? And so you take any vector in your space, add the zero vector, and you get your vector back. That's called the additive identity, because if I add it, I get the same value back. Also, number 5, if I use a -1 times a vector and add it to this vector itself, I'm going to obtain the zero vector. That's the additive inverse, in other words, the opposite of it. The scalar multiple of a vector is a vector that's in the same space. It's closed. Under scalar multiplication, we talked about closed a little while back. If you have the scalar multiple of the sum, it is the scalar multiple of each vector with those two vectors added. So you're distributing the scalar. Also, if you have the sum of your scalars times a vector, the vector distributes to the scalars, right? So that's also a distributive property. Number 9, associative property with respect to your scalars. I can multiply through the d in my vector and then multiply that answer through by c, or I can multiply the c times d and then distribute through my vector. I'll get the same answer both ways. And the last one is 1 times your vector is your vector, and that's the scalar identity. A lot of the spaces that you're going to check, if they're matrices, then the properties of matrices will take care of almost all of these axioms. A lot of times all you have to do is prove that something's closed under addition and it's closed under scalar multiplication, because of the rest of the axioms kind of take care of themselves. I did give you an example where multiplication is redefined and went through all the axioms and showed you where it fails to be a vector space. It was kind of, not an easy problem, but you need to get used to proving things and checking all of the possible situations. Okay, for an example, take the set of all 3 by 2 matrices. If you add 3 by 2 matrix to another 3 by 2 matrix, you're going to get a 3 by 2 matrix. So it's closed under addition. If you multiply a 3 by 2 matrix by a scalar, all you're doing is distributing that scalar to each of the elements in the matrix. Therefore, it's closed under scalar multiplication. And if you look back at the matrix chapter, theorems 2.1 and 2.2 take care of all the other axioms. And so the set of all 3 by 2 matrices is a vector space because it's closed under addition and scalar multiplication, and it has the properties of matrices. Okay, so a list of the common vector spaces like R2, R3 are in under standard definition of addition and scalar multiplication is on page 163. Okay, let's check out this this example. The set of all polynomials of degree 3. Think about that. If I have 2 polynomials of degree 3 and I add them, do I get always get another third degree polynomial? Well, look at my example down here, right here. If this is a third degree polynomial, this is a second degree polynomial. Yeah, let's change the notes. Sorry. Of degree 2. I really did intend for this to be a third degree 2. Okay, so in this case, I have a second degree polynomial and a second degree polynomial, but when I add them, I don't have a second degree polynomial. I have a degree that's less. So because the x squared's canceled, right? So this is not a polynomial of degree 2. So it is not closed under addition and therefore not a vector space. Okay, what about the second problem? The set of all polynomials of degree 2 or less. If I have degree 2 or less, it is a vector space. I'm never going to end up with a higher power of x under simple vector addition or scalar multiplication. I may lose a power somewhere when I'm adding, but I'm never going to gain a higher power. So if I say degree 2 or less, that becomes a vector space. Do you see the difference in those two sets and why one is and one isn't? And it's something as simple as saying or less. Okay, I have no idea why the center of this screen is fuzzy. I hope you can see it. I'll zoom in as I'm talking about it. How's that? It probably won't help, but whatever. Okay, determine whether the set R2, this is real numbers in the plane, XY plane, determine whether it's a vector space if addition is redefined to where we add this point to this point, and instead of getting x1 plus x2, we have them multiplied. So we've redefined addition. Scalar multiplication is the same. Okay, so let's see what happens. Remember, we're multiplying instead of adding. We redefined it just for kicks to see if it is, sorry, I can't make it that big, just to see if it is a vector space. So let's go over some of the axioms, and I'm doing them a little out of order because I wanted to do closed under addition and closed under scalar multiplication first, because if those are usually the ones that you're going to need to check. Okay, so let's see. If I have any two points on the plane where x, any two values, that's why I have an n here, all of my components in my points are going to be real numbers, right? So they're multiples. Their product of any two real numbers is also a real number. So the sum, the newly defined sum, is also real numbers. So it is in R2. That means anytime I add two of these points under this new definition, I still have a real point on the plane. And so it's closed under addition. Scalar multiplication, I just multiply each of the components by the scalar. Because c is a real number and all of my x's and y's are real numbers, then this guy is in R2, so it's closed under scalar multiplication. This axiom right here, if I have the first point times the second point is going to be the same as the second point times the first point, right? Or added. U plus V equals V plus U, sorry. Because when I add under this, hold the phone, under this definition, if I add these in the opposite order, I get x2, x1, but they're real numbers, so it equals the same thing, right? Because each of the points will be the same, whether it's x1, x2 equals x2, x1, or y2, y1 equals the y's, right? So it doesn't matter which one you multiply first. The next axiom, I can group the second 2 points, or I can group the first 2 points. Try it, you'll see that it is associative as well. This is commutative, this is associative. I didn't write it down in a very good way, but I knew I was going to run out of room, sorry. There exists a 0 in R2. That's a big one. It is there, it exists. Okay, moving on. If I add the 0 point to any point, I get, in this case, the 0 point. And that's not what the axiom says. The axiom says that any vector plus 0 has to be the vector itself. And it does, in this case, because x1, x times x2 goes here, it goes to 0. So it does not equal the point itself. So it fails the additive identity. So it is not a vector space. If you're showing that something is not, you only have to come up with one reason. I just wanted to show you more than one. In this case, when you have a point and you add its opposite, you don't get 0, 0. So it fails the additive inverse property. If we have a scalar multiple of a sum, we're supposed to be able to get the c times the first plus c times the second. And then if we use the continued distributive property in here, we would get c multiplying twice, which would be c squared times each of the pieces. Whereas by this definition here, the sum, if we start on the inside here, the sum of those two, it gives you this new point, and each of these things is multiplied by c. Do you see what I'm saying? If we distributed first, we would have this, and then c times this plus c times this gives me this, and when I add these under the new definition, like I said, I get c squared instead of plain c. So it fails at that distributive property, and it fails at the other one too. I'll leave that to you to do for yourself to see. But that is an example of a question asking whether something is a vector space if you have redefined addition or scalar multiplication. So try the homework. I believe the homework was listed on the first page, and I'm going to also put the homework for the whole unit on black canvas under homework. You got to scroll way down to find it, but it should be there.